Rob here, and from Get Some Systems, we're going to go over the more of the functionality of the firmware for this MSP, for this toaster project. And the first thing we'll start with, I guess, is the capture compare register that handles all of our temperature stuff. So when you configure this, you configure it with these, actually I think it's in here, define set temp 1, 2, and 3. And you saw in the demo we went to 140, held for 45 seconds, 170, held for 45 seconds, then we went to 215 and held for 60 seconds. So these are where you set the temperatures. I had 3. You could change the algorithm up a little bit and add more or less, but I want 3, so I wrote it up for 3. So that's where our set temperature that you'll see for this interrupt service routine comes in. So this is our capture compare register 0. Remember, we count up to this with timer A0, and it interrupts 50 times a second. Not really necessary. I'm using it twice a second because I'm actually using a half a degree C, which you'll see later on in the ADC service routine. I'm actually calculating sample temperature in 1 degree C and 1/2 degree C, and so I interrupt twice a second and check with a resolution of a half a degree C. So I did this by creating one big if statement in here that counts up to 25. Remember, we're interrupting 50 times a second. It counts up to 25, and then it executes our state machine. So this is just a simple state machine. It's temp state is our state variable. Our first case 0, this is initialized to 0. And case 0, we just check to see if the system's powered up and starting fresh. If it is, we set our temp last value equal to our average half temp. So this is the half degrees C. We set the temp last value, and this variable allows us to keep track of the last temperature to see if we're increasing or decreasing, because we compare the current temperature to this temp last value. So all we do is set that and go to the next state. In the next state, this is where we have our ramp time. If the final temperature is greater than or equal to the target temperature, then we know we're good. We've reached our target temperature, our first target temperature, and we move on. And so final temperature is initialized to 0. Actually, final temperature is the variable that you'll see how we calculate that in a second. But basically, we take the thermocouple temperature and room temperature from our ADC10 interrupt routine and process that to create a variable that holds the real temperature from the thermocouple inside the toaster, measured in degrees C. So if the toaster is at 100 degrees C, our final temperature is 100 degrees C. And if that's greater than or equal to our target temperature, then we'll go to the next state. If it's not, and it's not in the beginning, and that's why you see us increase temperature until we get there, we're going to check and see if average half temp is greater than temp last value plus 1. So we check to see if we're incrementing at a half a degree C per a half a second or greater. If we're increasing faster than that, we slow our pulse width duty cycle, our duty cycle for our PWM down, because I only want to increase at 1 degree C per second. So if we're increasing at 1 degree C per second, here it's actually checked at 1/2 degree C per 1/2 second to give us a little more accuracy. Then we decrease our duty cycle. If we're not ramping up at a degree C per second, then we increase our duty cycle. And you see in the demo, we really run up to our main duty cycle, or our max duty cycle, and sit there because we don't increase at more than a degree C per second. And so if our final temperature is not greater than or equal to our target temperature, which on the first ramp is 140, then what we do is stay here at our increase PWM displacement that will increase up to our maximum set duty cycle, which is software configurable, which we'll see later. And we sit there. Once we reach our target temperature, we change state, exit this, and go on to the next state. This if statement right here only makes sure that we don't increase at anything greater than a degree per second. Once we reach our temperature, we jump down here. We wait 1 second or 2 counts, since we interrupt every 500 milliseconds. Once we wait 1 second, we shut down our PWM, and this is done to help prevent some overshoot. You can see in the demo there's a little overshoot every time we hit a temperature. We go about 2, maybe 3 degrees over. This shutdown basically buys us some time to kind of smooth out that overshoot, and we increase a shutdown PWM count so that we can count up our 1 second delay, and if we haven't reached our 1 second delay, we stay here and just keep executing this if statement, shut down PWM and increment our counter. And this happens twice a second, so all we have to do is count to 2. That gives us our 1 second. Once we get to 1 second, we change state, reset our counter, and our check temp rise time equals final temp. And so this is kind of similar to what we had before, where we store the last temp to make sure we're increasing and decreasing. We store our current temperature in check temp rise time, because remember, we've been increasing, we've overshot our temperature a little bit, so we turn off the oven and we're letting it kind of cool off to help prevent too much overshoot. And so what we want to figure out is we want to figure out when our temperature is actually decreasing and coming back down towards our target. And so that's what this does. We set our check rise time to our final temperature, and then what we do is we check our current temperature against our rise time temperature, and as long as it's continuing to heat up, we'll see that final temperature is greater than check rise time, which was our last temperature, so we stay in state 3 and we stay powered off. So effectively what this does is, once we have overshot our temperature, we basically shut off and wait until our temperature starts decreasing instead of increasing. And then once it's decreasing, we see that, we reset our check temp rise time, and we don't use this anymore, I don't think. This is just good practice. Reset your flags and variables and counters, and then we change state. And this is just checked every second. That's what this shutdown PWM count allows us to check this every second instead of twice a second. And so what we have to do is we have to see the final temp drop lower than the last temp in every time we check it, which would be once a second. And so once we see our temperature decreasing, we go to the next state, clear out our variables in that state, and in state 4 we basically just hold our current temperature. And the way this works is, if our final temp, which is our current thermal temperature in degrees C in the oven, if that's greater than our target temp plus 1, we decrease our duty cycle till it gets to 0. So what happens on the demo is you'll see us overshoot our temperature, wait till it starts decreasing, and then go to this state. And then in here we wait until the temperature is not greater than our target temp plus 1. So for 140, we basically see us overshoot 140 in case 3, and then we wait till our temperature starts decreasing. When it does, we go to this state and we wait till our temperature decreases to 141. Once it gets to 141, we go down here and see that our final temp, or our current temperature in the toaster, is less than our target temp plus 1, which would be or equal to 141, and we start powering up the toaster, increasing our duty cycle, and that allows us to get a jump on this falling temperature and gives us a lot smoother profile. So effectively what happens is, we're heating up here, we get to 140, we shut off. Once we get to 140, we shut off for 1 second, and then after that 1 second we come down here and we wait till our temperature starts coming back down and decreasing. Once we see it decreasing, we go to this state, we wait till our temperature goes under 142, it's either equal to 141 or 140, and then we start powering up our toaster to pulse width modulate power to the toaster to hold it at 140, 141. And this is pretty accurate. As you can see in the demo, this works pretty well. So it just waits basically to see when it gets to 141, it knows it needs to start powering up, and then about a second later we've got a little bit of power to kind of start warming things up. And we sit here in this state, controlled by this if statement down here. This is what controls whether we stay in this state or reset this state machine. And so if the temperature is holding, it's only going to fluctuate a couple degrees. So if our current temperature in the toaster, final temp, is less than our target temp minus 10, then we go to state 0 and restart. So basically what that's saying is if our current temperature is less than our target temperature minus 10, then we go to the next state. Basically, if you change target temperature, which you'll see in the state machine above, this will make more sense. If we go from 140 to 170, right, 170 minus 10 is 160, so final temp, which is going to be 140 because we're currently at 140, and we want to go to 170, we see that this is true. Final temp is less than target temp minus 10, so we go to the next state. If it's not, then we stay here and regulate. So really what happens is when we hit 140, we make our way down here, and this is how we get our hold times or our soak times, is we see that our current temperature in the oven, 140, is not less than our target temperature, which is still 140. For that 45 seconds, target temp stays 140. We see that this isn't true. So we stay in this state, temp 4, and continue to regulate. Once we change our target temp to 170, we see that this is true, and we restart this algorithm, which again goes back to case 0 and runs through all this again, so it ramps up to our next new temperature and then holds. And so this is the algorithm that we use to ramp up and hold our temperatures. And this way, this interrupt service routine takes care of all that for us. In our main program, all we have to do is set target temps and set our pulse width modulation displacement value, that's how much we want to add to the duty cycle, or effectively add to capture compare register 1 in timer A1 to increase our duty cycle pulse width every time. So if this is 100, every time we execute one of these functions, increase duty cycle, we're going to add 100 to CCR1. And as you'll see, when we need to increase temperature a lot faster, we'll increase this. So every time we execute this, we might add 500 or 1,000 or 10,000. And so that's the algorithm used here to control temperature. And this allows us in our main program to just set the temperature and let it run. And down here is just some maintenance, pretty straightforward. Here's where we blink our LED to make sure our temperature regulation is still working reliably. Real quick, this is our RX interrupt routine for the UART, and when we receive a byte, we interrupt and check the byte. If the byte's a 77, then we start our thermal cycle, and this gets set to a 1. If you go up to our main state machine in our while loop, right here, it does a switch. If our start thermal cycle is 1, then we begin the state machine with these settings and continue to run, and this runs through the entire thermal profile. But that's when you see me click run in the demo, this is what I'm doing, sending a 77 to start this whole process from the very beginning. We've gone over our TX. This is not really used. You actually don't really need this. This is the interrupt service routine for the PWM signal, but you don't really need to service an interrupt routine since it's this is CCR0. Yeah, I just put this in here because I had interrupts on for CCR0 and I didn't want to get any errors or anything, so it was just a simple quick development fix, so I didn't have to worry about any of those bugs.